Now that we've completed the definition of the information needed for the aerogeometry file, we'll move on to mesh settings. The first thing to do is to specify the mesh type. Though we offer a number of different mesh topologies from which to choose from, we strongly recommend that you stick with OHH mesh for 2D analysis. OHH mesh provides more uniform mesh distribution at the leading and trailing edges, which leads to better insight into the flow physics at both locations versus OH mesh. You'll also need to select a mesh smoothing algorithm. We recommend defaulting to the Laplace option if you're using OHH mesh, as it helps to capture more detail of flow physics. But if you've selected one of the legacy mesh topologies, use the Poisson option. Mesh fan-out and clearance meshing aren't relevant for 2D analysis, so take the defaults, which is no mesh fan-out and no clearance meshing. You can also indicate how meshing will be handled close to the walls. By default, we assume wall integration, but you have the ability to choose an input wall function or a coarse mesh wall function should you so desire. The next step is to specify the granularity of the mesh that will be generated. There are a number of presets that we've provided that work well for us, anything ranging from extremely dense and finest granularity to coarse meshing. Alternatively, you can also be explicit about how many mesh points you want to have across various sections of the flow field. For example, you'll be able to specify the number of mesh points from the leading to the trailing edge of the airfoil, from the hub to the tip of the airfoil, from the upstream boundary to the leading edge of the airfoil, from the airfoil trailing edge to the downstream boundary, and across the airfoil pitch. In our situation here, we're just going to take the default setting, which is fine. Finally, if you'd like to visualize the generated mesh, you can select through the mesh plot format, the proper format you desire. In our case here, we'll just choose TechPlot. Okay, so we move on now to the final step, which is to configure solver settings. A couple things we have to do here. First is we need to define the flow simulation model to be used. We've got a couple choices: laminar flow, turbulent flow with Wilcox's transitional model. Generally speaking, most of the time you'll end up using turbulent flow, and you'll want to use the transitional model if the Reynolds number is really low, say less than 4,000. Okay, in our situation, we're going to use the turbulent flow model. You'll always want to take advantage of convergence acceleration. It has a major speed up in the execution times of your runs. And you'll be able to specify the heat ratio model that you'd like to use for the simulation. You can use a constant value, you can use the variable gas properties of air, or you can even enter a custom mix of theoretical air with fuel. The next thing we'll need to do is specify some execution parameters. The first, the most important, is the number of iterations to execute. For 2D analysis, we recommend the value of 4,000 iterations. And you'll also need to specify the number of iterations between printouts of performance data. We recommend an interval of 50. Next, you'll be able to specify the number of iterations between file generations. We recommend generating restart files every 100 iterations. And if you desire a mesh plot, then you can specify the format here. All right, so there you have it. We've just configured a 2D simulation run. And when we're complete, we'll click on Finish to begin the process of generating the files. So what the Workbench next does is it takes the information you've provided in the wizards and generates all of the setup files and the scripts for local execution. We can see this through the console window. In our situation here, we've just built a case called VKI Vein2D, and it's gone through the process of importing the geometry data, doing some data validation, generating the AGF, generating the WAN setup file, and generating the LEAP setup file. One way we can tell the build is successful is by taking a look at the case folder that we created called VKI Vein2D. Sure enough, we see a number of files here: the case file, which is the XML file, the 3 setup files required by Leo and Wand to execute, the aerogeometry file, the Leo file, and the Wand file, and the 2 execution scripts, runleo.bat and runwand.bat, to invoke the solver and generate the mesh, respectively. Now, if you're running Linux, you won't have bat files, you'll have .sh files, but it has the same purpose, and that is to invoke local execution of your simulation runs. Now that the files have been generated, we're ready for execution. We'll go to the editor view for this. There really are 2 steps. The first is to generate the mesh with the initialized flow field using the generate mesh link, and then to actually invoke the solver by clicking on the run Leo solver link. Now before we do that, why don't we make a quick modification in the case in order to change the iterations from a 4,000 iteration count down to something smaller like 400. To do so, we'll go to the editor view and click on the modify case link, which opens up the wizard, allows us to quickly get to the parameter we wish to change, which is iterations to execute, and to change that to 400. Once we've made the necessary change, we'll click on Finish, which will generate the files for the case, update those files under VKI Vane. So with that completed, let's go ahead and generate the mesh and run the simulation. So by clicking on the link, the mesh gets generated. It happens pretty quickly, you can see here for this case. And in order to demonstrate that it is run successfully, we'll refresh the workspace and look for the existence of an initial binary restart file. That is of the name VKI-Vane2D. It in fact exists along with some additional diagnostic information, and that tells us that we're ready to go off and invoke Leo. To invoke Leo requires both the restart file and the setup file. So we run Leo, and this will initiate Leo with all the parameters and information that we've provided it. It will allow you to track convergence history on a periodic basis. That can be done so by refreshing the workspace and to look at something called convergence file. If you look at the convergence file, then you can see here that we've actually successfully run 400 iterations in a fairly short period of time here. All right. So in a nutshell, this is the entire cycle from setting up parameters through the execution of a 2D single row steady run. Now most of you will likely be using 2D analysis for airfoil design, and that'll include both varying airfoil geometries as well as changing factors like back pressure or flow angles to predict performance across a range of conditions. The good news is that you don't have to go through this process for each iteration. Instead, you can utilize the new from existing capability in the wizard to speed your iterations along. Let's take an example of this. So in order to take advantage of it, what we'll do is we'll go off and we'll create a new simulation like we did for VKI Vane 2D, and we'll name the case test case. And instead of building it from scratch, we'll click on this box called Use Setting from an Existing Case. In this situation here, we'll select the case VKI Vane 2D and associate it to my project again. Now, what happens now is that the wizard will automatically populate this case with all of the parameters from the VKI Vane 2D case, leaving me with just the mods that I need to make for this particular simulation run. So it might be that I want to associate this to another geometry, an airfoil geometry, or it might be that I want to simply change the back pressure from 15.4, let's say, to 14.8. Whenever I finish my change, I'll click on Finish, and my second run is now complete. A lot faster with no need to re-enter in the data. So there you have it. 2D cascade simulation in a nutshell. We've showed you how you can take advantage of the wizards, of the automatic file setup and local execution script setup capability built into the Workbench, and the ability to actually perform the execution through the editor view. By using the new from existing capability, you'll be able to iterate very quickly on the variations that are inevitable as you go through airfoil design. Thank you.